Hi dear students, this lecture is organized on behalf of Department of Chemistry to understand the concept of reagent and catalyst in organic chemistry for the third year BSc students. So in the previous lecture we study about catalysis. Now in this lecture we can study about the reagents. Let us see what is reagent. Reagents are the compounds that are added to a system in order to cause a chemical reaction. Or reagents are not necessarily consumed in chemical reactions. Reagents are used to measure, enhance or initiate a chemical reactions. So I think you all are aware about this well-known chemical reagent, that is Grignard reagents. When the Grignard reagents reacted with the aldehyde or ketones, it always gives secondary or tertiary alcohol, and when the Grignard reagent is reacted with the ester, it always gives a tertiary alcohols. So Grignard reagents are extremely useful organometallic compounds in the field of organic chemistry. So they exhibit a strong nucleophilic qualities and also have the ability to form new carbon-carbon double bonds. Similarly, Tollens reagent refers to a chemical reagent which is this is the Tollens reagent which is used in the detection of aldehyde functional group, an aromatic aldehyde functional group, or an alpha hydroxy ketone functional group in a given test substances. When this aldehyde is reacted with this Tollens reagent, it always produces this acid. So the reagent indicates which type of substance is present in the chemical reactions. So this is all about the. So there are wide variety of reagents in the organic chemistry. We are going to see only few of them. So the basic difference between the catalysis reagent. In the last lecture we studied about the catalysis. Now in this here it is we are going to study about the reagents. According to catalysis, catalysis is a substance which accelerates the rate of reaction without consuming. It can be regenerated, but the reagent it cannot be regenerated. It can be consumed in the reaction. So that is the basic difference. Catalyst cannot be consumed in the reaction, but reagent has to be consumed in the reactions. See these two reactions. This is simple acetophenone. Where when we are going to reduce with the palladium catalyst, it gives this aromatic alcohol. Similarly, this acetophenone is reacted with the sodium borate. It gives same product alcohol, aromatic alcohol, but side by it gives this boron and NOS. So this is the waste. This is just waste. It creates a byproduct, while here it is no waste. So catalysis are always prefer as compared to the reagent because it does not create any kind of waste. This is the basic difference. When we are going to use a reagent, it always produces weight, while catalysis do not produces weight. Catalysis can be regenerated in the reaction, while the reagent will never be regenerated in the reaction. Let us see the first reagent, that is sodium borate. Here you can see the structure of sodium borate, sodium being a positively charged and the boron being a negative charge. So the four hydrogen atoms are attached to the boron atom. So actually sodium borate acts as a mild reducing agent. Why it is a mild reducing? Because the boron because the boron and hydrogen bonds are very strong bond. These bonds are very strong bond. So due to this, these are strong bonds. Due to this, the cleavage of between these two atoms requires high energy. So it is slowly dissociates. So the hydride ion will come very slowly. That's why it acts as a mild reducing agent. The sodium borate are soluble in polar solvent just like as methanol, waters, alcohols mostly. So as per I said, it is a strong hydride ion donor. Due to this mild reducing agent, it acts as a chemoselective agent. Why it is chemoselective agent? Because of its mild reducing property. Suppose any molecule containing both the carbonyl groups means aldehyde as well as ketones. So this is aldehyde and this is a ketone. So when we are going to treat it with this particular moiety with the sodium borohydride, it only reduces this molecule, this into corresponding alcohol. It cannot reduce as ketone because the reactivity of aldehyde is more as compared to the ketone. So that's why it's a chemioselective reagent. Let us see some examples of sodium borohydride. So this is an aldehyde. This is 1, 2, 3, 4. This is a butanaldehyde. When reacted with the sodium borohydride and methanol as a solvent, general alcohol being a solvent, and it always gives a primary alcohol. This particular aldehyde gives a primary alcohol. If you look at this particular carbonyl group, this C double bond OH group is always converted into the CH2OH group in case of aldehydes. Students should remember that this particular aldehyde group is converted into the CH-OH group when we are using sodium borohydride. Similarly, in the case of ketone molecules, so this is a ketone 1, 2, 3, 4, 5, 5. This is a 2, 2 pentanone. When 2 pentanone is reacted with the sodium borohydride, alcohol being a solvent, it always gives a secondary alcohol. So the ketones are always give secondary alcohol. Similar way, in case of ketone, this carbonyl group is converted into this particular group, CH-OH group. Again, students should remember these things. So in case of aldehydes, sodium borohydride gives a primary alcohol, that is important thing, and in case of ketones it gives a secondary alcohol, that is again important thing. As per I said that this sodium borohydride is a chemioselective reagent. Here you can see, here these are the two function groups. This is ester function group, this is ester, and this one is a ketone functional group. This is a ketone functional group. When this particular moiety having two different functional groups reacted with the sodium borohydride, it gives this product. Here you can see only this particular functional group is reduces into the alcohol, means ketone is reduces into the alcohol rather than ester, because ketone is a high reactive as compared to this ester. So the sodium borohydride first reduces the ketone and then ester. So the sodium borohydride is a chemioselective. If any example, if example having ketone as well as aldehyde as a functional group, if we reacted with this molecule with the sodium borohydride NaBH4, so that reduces only this aldehyde rather than this ketone, because aldehydes are more reactive as compared to the ketone, but it reduces aldehyde into corresponding alcohol and then ketone. The next reagent is, second reagent is lithium aluminum hydride or red alumina. Here you can see the structure of both. This structure is belongs to the lithium aluminum hydride. The first structure is belongs to the lithium aluminum hydride, and the second structure belongs to the red alumina, which has IUPAC name sodium base 2 methoxy ethoxy aluminum hydride. So both are the very strong hydride ion donor, because the bond between aluminum hydride, in case of the bond between aluminum hydride, it is a weak bond. So it is a weak bond. In both the cases these bonds are weak, so they act as a very strong hydride ion donor. So there are many similarities between these two reagents. So both the reagents are strong hydride ion reagents which reduces polar unsaturated carbonyl groups such as carbon oxygen double bond, carbon nitrogen triple bond, carbon nitrogen double bond, nitrogen oxygen double bond, etc. They do not reduces non-polar unsaturated groups like carbon carbon double bond, carbon carbon triple bonds, as these alkynes are always unaffected by these reagents. Both the reagents, both are the non-chemoselective reducing reagents. Hence it is difficult to reduce only a carbonyl group without affecting the other groups. So it is not a chemioselective reagent. It is very strong reducing agent, so it is not chemioselective reagents. So these two reagents have some basic differences. Lithium aluminum hydride is a white solid or a gray if impure. It is insoluble in many organic solvents except ether and THF, while red alumina is a solid soluble in aromatic solvents. In fact, it is used as a 70% solution in toluene. While lithium aluminate reacts vigorously with water, it is used in dry ether or THF as it is sensitive to moisture. But the solution of red alumina is more stable in air and moisture than this. So the lithium aluminum hydride is inflammable on exposure to air, whereas the red alumina is thermally stable up to 200 degrees Celsius. Both the reagent reduces aldehyde, ketones, acid, chlorides, esters, cyanides, and nitro groups, but the red alumina is found to be more efficient reducing agent. So aldehydes and ketones are reduces into corresponding alcohols. The unsaturated aldehydes and ketones gives unsaturated alcohols. Let us see the example of both the reagents, lithium aluminate and red alumina, both having the same functionality, but the red alumina is more effective as compared to the lithium aluminate. So this is an aldehyde molecules, unsaturated aldehyde molecules having double bonds. When reacted with both the reagents, lithium aluminate or red alumina, it gives corresponding unsaturated alcohol. So it only reduces this. Sorry, it only reduces this carbonyl group into the corresponding alcohol group. So the carbonyl group is converted into alcohol group. Similarly, this highly substituted carboxylic acid is reacted with the lithium aluminate or red alumina. It gives corresponding alcohol. So this carboxylic group is converted into the CH2OH group, that is alcohol group. Similarly, this acid chloride is also reacted with the lithium aluminate or red alumina. It gives corresponding alcohol. So the beauty of this reagent is it reduces all kind of functional group into the corresponding alcohol, all kind of carbonyl groups into the corresponding alcohol, whether it is aldehyde, whether it is ketone, whether it is acid, whether it is acid chloride, or whether it is acid anhydrides also. So the lithium aluminate and red alumina, both the reagent reduces acid derivative into corresponding alcohols. So this is the amide which is going to convert it into alcohol. Similarly, this cyanide is going to convert it into the alcohol. Here you can see this particular amide group is converted into the corresponding alcohol group, and this cyanide group is converted into the corresponding cyanide group. So student, remember these things when we are going to use a lithium alumina hydride or red alumina. So it directly reduces the any kind of carbonyl group into corresponding CH2OH group, whether it is aldehyde, ketone, anhydride, cyanide, or anything else. The next reagent is MCPB, which is nothing but the metachloroperbenzoic acid. This is the structure. This is the structure of metachloroperbenzoic acid. Actually, peroxy acid is a carboxylic acid with OOH instead of OH. In case of carboxylic acid, there is OH group is there, while in this case this OOH is there. So this is the little bit difference between these two molecules. Actually, MCPB is a colorless crystalline solid containing 80% active paracid. It is a specific reagent for oxidation of alcohol into the epoxide. The general purpose of this MCPB is for the epoxidation of alkene compounds. It is also used in the Baeyer-Wallis rearrangement reactions. So the how that epoxidation takes place is explained in a single step reactions. Generally, when we are going to for the mechanism, in case of MCPB, this oxygen which is highlighted in green, it is electron deficient oxygen. It is a deficient oxygen, and due to this deficiency it easily attacked by the alkanes molecule. This carbon-carbon multiple will easily attack here. This bond migrated here, becomes carbon-carbon double bond, and then this carbon-oxygen double bond becomes a single bond here, and this bond migrate to this hydrogen, and this hydrogen and oxygen double bond donates both the electrons to this carbon, make it epoxide. So this is how the transition state takes place, and when the transition state collapse, it forms a epoxide. If you look at this, due to this electron deficiency of this oxygen, epoxidation will occur only at the only on those double bonds which having high electron density, means the multiple bond should substitute it with the high electron donating groups, and then epoxide will easily carry out. And one more thing is that the epoxidation, the addition of oxygen or insertion of oxygen takes place from the same side. So it is a scene epoxidation. Epoxidation always occurs in a scene because the oxygen is added from the same side. As I am said that the epoxidation always occur from the same side. Let us see the examples of epoxidation. When the molecule having transalkanes, and in that case the epoxidation always shows a trans product. The addition of oxygen is always from the same side. If you look at this, the addition of oxygen is always from the same side. It shows both the bonds of oxygen from the same side above, so thick line represented. So it is addition of same side, but trans isomer always gives a trans epoxide, and there are side byproduct is there metachloroperbenzoic acid. We are not interested in this, but when if we consider trans alkene, it always gives a trans epoxide, and which is a mixture of enantiomers. Note that this is a very important sentence. So if we take cis alkane, then it always gives a cis product. It always gives a cis product with this byproduct. It always gives this cis product with this is the byproduct. So here it is again, the oxygens double bond of sorry, these two bonds of oxygens are added from the same side, so it is a cis addition, syn addition. But when we are going to consider cis alkane, is always gives a cis product. So cis product, depending upon these two alkyl group, the cis product may be meso or not meso. If these two groups are identical, the molecule becomes symmetrical, so it becomes a cis, so it is inactive. Let us see the example of epoxides. So this is a cyclopentene. When cyclopentene is subjected with the MCPB, it gives this kind of epoxide. The double bond is converted into the corresponding epoxide. So the oxygen is inserted in between these two carbon double bond and forms a three-member cyclic system. So this is the general epoxidation. If you consider another example, so this is the example which having two double bonds in the same cyclic system, but one double bond is highly substituted, another one is less substituted. This double bond is highly substituted and this double bond is less substituted. So epoxidation will occur two different ways, because the molecule contains double bond, and when the moiety is reacted with the epoxide MCPB, it always form epoxide. So this double bond may also form epoxide like that, and this multiple bond also form epoxide like that. So out of this, one is major, another is minor, because in case of MCPB, the oxygen is electron deficient. That oxygen is added only at the double bond which has high electron density. If you can see in these two double bonds, only this double bond having highly substituted groups. So this is a methyl group, this is methyl group, this is methyl group, this is a methyl group, and these are electron donating groups. So they increase the electron density here, while there is no such type of groups here. So no such type of groups here, but here two groups are there and which are electron density, so they are increases the electron density at this particular double bond. So the epoxidation will occur on this multiple bond rather than this one. So the actual major product, this is the major product and this is the minor product. So students should always think about that when they are observing the reaction. In this case, if there is a multiple bond, which bond is highly substituted with the electron donating group, and then they think about that this can be goes for the epoxidation. Hi. Next reagent is selenium dioxide. Selenium dioxide is a white solid which is soluble in solvent like diaxone, ethanol, acetic acid, acetic anhydride in water. Selenium dioxide is extremely poisonous and hence proper precautions should be taken while working with it. It is a chemoselective oxidizing reagent. It selectively oxidizes active methyl or methylene groups as well as allylic groups without affecting the carbonyl groups. The stronger oxidizing agent like CrO3, KMNO4, etc. will cleave the molecules, but it won't be cleaved, it selectively oxidizes the molecule. So let us see example. So this is a cyclohexanon which when subjected to the selenium dioxide, it oxidizes into the corresponding carbonyl group, dicarbonyl groups. So this particular methylene group is oxidizes into the corresponding carbonyl group. So let us say another examples. So this acetaldehyde molecule when subjected to selenium dioxide in presence of solvent ethanol, it gives corresponding diol. This particular methyl groups, this is active methylene group because it is next to this carbonyl alpha methylene group, so it is active methyl groups, so it can oxidizes into corresponding aldehyde. So selenium dioxide always oxidizes the active methyl methylene groups into corresponding carbonyl groups. Let us say another example. This is a ketone molecule which is subjected to this selenium dioxide, and in this case this active methyl group is oxidizes into the corresponding aldehyde. So as earlier I said that the selenium dioxide always oxidizes active methyl groups next to the carbonyl group into corresponding carbonyl. The sentence is that those active methyl group are oxidizes into the carbonyl group which are next to this carbonyl and which is next to this, that's why it is oxidization to the corresponding carbonyl. Similarly, this is the carbonyl group and this methyl group is next to the carbonyl, means alpha group always oxidizes into the carbonyl corresponding carbonyl by using the selenium dioxide. So this is another kind of examples. So these are the allelic groups. Allelic groups can be hydroxylated. Allelic groups, these are the allelic groups. Allelic groups can be hydroxylated at the allelic positions. So first we have to find out the allelic position. Allelic position means the groups which are next to the double bonds. So this is the double bond olefinic carbon atoms. This is 1 and 2. For the consideration I am going to write down 1 and 2. So this methyl group is allelic, this methyl group is allelic, this methyl group is allelic. So these three methyl groups are allelic. So out of these three methyl group, any group can be oxidized into corresponding alcohol hydroxyl groups. So in case of allelic groups, when we are subject to these allelic compounds into to the selenium dioxide, these allelic groups are always oxidized into the corresponding alcohols. So in this case, this methyl is allelic group. This is also this, but we are going to oxidize only this. So this methyl group is converted into the corresponding CH2OH group. So students should remember that in case of allelic groups, only those allelic groups are oxidized into the corresponding alcohol. Suppose if there are alternatives, means more number of allelic groups are there and more substituted compound is there. So in this case the hydroxylation takes place at the alpha position to the more highly substituted end of double bond. See in this case this is a carbon carbon double bond, so these two groups are olefinic carbon atoms, and now this is allelic group, this is allelic group, and this is also allelic group. So the oxidation can occur at this group also, at this group also, at this group also, but the product shows that this group will be oxidized easily, because if you look at this side, this olefinic carbon is substituted by only one methyl group, while this olefinic carbon is substituted by two methyl groups. So this methylene group is oxidizes into corresponding alcohol groups, this alcohol groups. And the last reagent is N-bromosuccinamide, NBS. So this is the structure of NBS. Actually NBS is used in radical substitution and electrophilic addition reaction in organic chemistry. NBase is a convenient source of Br radical, and it is a specific reagent useful for allylic brominations and benzylic bromation. So it is prepared by adding bromine to a cool solution of succinamide. It is prepared by adding bromine to a cool solution of succinimide when the NBS reagent is precipitated. So this is the simple preparation method of NBS, and it is a most useful reagent for the bromination purpose in case of organic chemistry. Let us see some example of allylic brominations. Allylic bromination is the replacement of hydrogen on carbon adjacent to a double bond or aromatic ring with the bromine. So this is the first example, that is cyclopentene. When subjected to the NBS at UV light, it gives corresponding 1-bromo-cyclohexane. So this is the byproduct. HBr and succinimide are the byproducts of these reactions. So actually what happening, this hydrogen, this is allylic hydrogen, which is replaced by the bromine radical, which is generated by the NBS. So it easily occurs. Let us see another example. This is the toluene. When toluene is subjected to this NBS at UV light, it gives a corresponding bromobenzyl compound. This is bromobenzyl compound, and this is the byproducts. So in this case, similar way, this methyl group is allylic to this double bond. So allylic methylene group is also brominated by this reagent. Let us see more examples from the bromination case by using NBS. So this is another example. This is similar to the cyclopentene as we considered earlier. This cyclohexane is subject to the NBS. You can see these are the two positions for the brominations, because these are the active methylene position. Next to the double bond, these are always active positions. So in this case, these two positions are active. The bromination will occur here or here, but in this given product, the bromination occurs at here. Student can write down here also. Similarly, this next molecule, this is heterocyclic compound having the side chain methylene group is. So this methylene group is this next to this multiple bond, double bond. So it can act as an active methylene group. So the bromination will occur here. So you can see here the bromination will occur here. Similarly, this is the trans 2-butene. When subjected to the NBS, it gives a brominated product here. So actually this molecule is asymmetric. You can see the bromination will occur here also, because both the position are next to the double bond. If you consider this double bond N, so this is the next to this one and this is the next to this one. So the bromination can occur here and here. Student can write down here also. Thank you.